Water is undoubtedly the most essential resource for our existence. It accompanies every moment of our lives. It circulates in rivers and underground aquifers, springs from natural sources, is found in the bottles we buy at the supermarket, or simply flows from the tap as soon as we turn it on. Drinking a glass of cool water when thirst grips our throat is such a simple, natural gesture. And yet behind this apparent obviousness lies a colossal amount of work. What many don't realize is that the water that seems so readily available to us doesn't always come from mountain rivers or melting glaciers. In a world where freshwater resources are dwindling in many regions, alternative solutions have had to be found. In several countries such as the United States, Mexico, Saudi Arabia, and Chile, enormous quantities of seawater are transformed daily into drinking water for millions of people. This technological feat makes it possible to supply arid regions where every drop counts. So how can millions of liters of salt water be converted daily into perfectly clean, clear, and completely drinkable water? That's precisely what we're going to explore together. We're heading to California on the shores of the Pacific Ocean, where one of the country's largest desalination plants stands, a colossal facility capable of producing over 190 million liters of drinking water per day. A veritable city of steel and pipes whose primary mission is to transform the ocean into a source of fresh water. From the moment the water is drawn from offshore to the moment it finally flows into your home, your kitchen, or your bathroom, we'll follow together every step this precious liquid, which you use every day without even thinking about it, goes through. Settle in comfortably. This journey into the heart of modern technology will show you just how much more extraordinary the process of accessing clean drinking water is than it seems. Salt water covers more than 70% of the planet's surface. It is one of the most abundant resources in the world. Yet all of this water is unusable in its current state. Drinking salt water would cause severe dehydration and could even be life-threatening. Transforming this water into fresh, drinkable water seems simple in theory, but in reality, it's a colossal challenge. The first obstacle is the chimney leading to the plant, and you'll see that this first step alone requires impressive infrastructure. Desalination plants are always located in the immediate vicinity of the sea. On the surface, they resemble vast industrial complexes, but underwater they stretch for several kilometers. Gigantic pipes, securely anchored to the seabed, plunge into the ocean to continuously pump immense quantities of water. These pipes are designed to withstand water pressure, ocean currents, corrosive salts, and even seismic activity, as many of these areas are located in active tectonic zones. Once drawn in, the water travels through underwater pipes connected to incredibly powerful industrial pumps. Imagine enormous turbines capable of drawing in the equivalent of dozens of Olympic-sized swimming pools every minute. The water then sometimes travels several hundred meters before reaching the treatment plant, where it finally begins its processing. To grasp the scale of what such a facility can accomplish, the Carlsbad plant in California treats over 190 million liters of water per day, the equivalent of 95 million 2-liter bottles of water. This immense quantity could fill several football stadiums every week. In some particularly arid countries, such as the United Arab Emirates, over 90% of all drinking water consumed comes from this process. There, without desalination, it would simply be impossible to provide enough water for the inhabitants. Once the water arrives at the plant, the gigantic process can finally begin. When millions of liters of water enter the desalination plant, the first priority is to remove everything the ocean carries: sand, algae, shell fragments, marine bacteria, plankton, and even sometimes tiny crustaceans. Imagine drinking a glass of water containing all of that. Not very appetizing, is it? The water therefore passes through a series of mechanical filters. The first filters are very wide and trap the largest impurities. Then, as the water flows through, the filters become finer, forming a progressive barrier. These filters, made of ultra-resistant materials, are designed to operate day and night. Some resemble large metal grids, others layers of porous material stacked in multiple levels. Their role is to ensure that only pre-treated water, free of particles visible to the naked eye, can proceed. During this stage, technicians continuously monitor the water quality and the condition of the machinery. Nothing is left to chance. The slightest increase in pressure, a slight discoloration, or the appearance of an unexpected particle can signal a problem. An undetected defect could damage the reverse osmosis membranes, expensive and extremely sensitive equipment. Once the coarse impurities have been removed, the water is finally ready for the most dramatic stage of the treatment, salt removal. The water is now clean but not yet drinkable. It remains salty. To transform it into fresh water, a revolutionary technology comes into play: reverse osmosis. The principle is fascinating. The water is forced through special membranes, whose pores measure only a few nanometers. These membranes are so thin that they only allow water molecules to pass through. Everything else, salt, minerals, ions, pollutants, remains trapped on the wrong side. Forcing water through these membranes requires enormous pressure, sometimes exceeding 70 bars. This is equivalent to the pressure exerted 700 meters underwater. Only oversized industrial pumps are capable of producing such force. At the outlet, the water obtained is almost completely fresh. Reverse osmosis removes up to 99% of the salt. What remains on the other side of the membrane is called brine. This is extremely salty water, much more concentrated than seawater. This brine is then returned to the ocean, but not just any old way. It is carefully diluted and released in areas with strong ocean currents to prevent it from disrupting natural habitats or damaging the marine ecosystem. Now that the water has been purified, a new series of steps begins to make it completely drinkable. Soft water isn't necessarily clean water. Even after reverse osmosis, traces of viruses or bacteria invisible to the naked eye can remain. And when it comes to public health, the smallest bacterium can become a major problem. To eliminate any potentially dangerous organisms, the plants use several disinfection methods. The first involves exposing the water to powerful ultraviolet rays. These rays destroy the DNA of microorganisms, preventing any reproduction. It's a very effective process that adds no chemicals and doesn't alter the taste of the water. Some plants supplement this treatment with a very small dose of chlorine or chlorine derivatives, just enough to provide additional protection during transport through the pipes. This dosage is carefully controlled and has nothing to do with the strong chlorine odor found in a swimming pool. The water is now sterilized, but it's too pure to drink as is. The next step is to remineralize the water. The reverse osmosis membranes have removed virtually everything: salt, impurities, but also essential minerals. Water devoid of minerals would not only be tasteless, but also unsuitable for daily consumption. To remedy this, precise doses of calcium, magnesium, or potassium are added. These minerals are essential for the proper functioning of our bodies. They strengthen our bones, contribute to hydration, and even improve the taste of water. Mineralization machines add these elements in quantities calculated to the milligram, following extremely strict health standards. This stage restores the water's natural balance, its neutral and pleasant taste, and its quality comparable to that of the finest spring waters. Before being allowed to leave the plant, the water must undergo a series of rigorous controls. Engineers take samples at various stages of the process and analyze them in in-house laboratories. They check for the possible presence of bacteria, chemical purity, mineral content, pH, conductivity, and even the water's transparency. Each parameter must meet very strict international standards. If everything is in order, the water is finally transferred to gigantic reservoirs, often buried underground to prevent evaporation and temperature fluctuations. These reservoirs act as buffer tanks to ensure a continuous flow in the pipes. From these reservoirs, the drinking water begins its final journey. It is injected into a vast network of underground pipes that run through cities, towns, industrial areas, and residential neighborhoods. Some of these pipelines run for hundreds of kilometers, passing through tunnels, valleys, pumping stations, and desert areas. Everything is designed so that the water arrives at your home with the same quality as when it left the plant. Once it reaches populated areas, the water passes through small monitoring stations that ensure nothing has been compromised along the way. Then it travels through the city's water system before reaching your tap. And there you have it. Now you know the complete journey of water from the depths of the ocean to the worms you're holding in your hand. The next time you turn on your tap, take a moment to think about it. The water you're about to drink may have begun its journey across the vast Pacific Ocean. Through a complex and ingenious process, this salt water has become one of the most precious resources in your daily life. Tell me in the comments, do you prefer to drink tap water or bottled water? If you enjoyed this documentary, don't forget to like, subscribe, and turn on notifications so you don't miss any of our content. But don't go away just yet, there's more. The rest of this video will be just as exciting, so stay with us until the end. Dry ice is an amazing material. It doesn't melt in liquids, but it generates a dense mist upon contact with water. It can instantly freeze a strawberry, solidify a dessert in seconds, or preserve vaccines in perfect condition for weeks. Unlike the classic ice cubes we use at home, this special ice isn't made of water. It's made of carbon dioxide. When this gas is cooled and compressed until it solidifies, it takes the form of a white substance reminiscent of ordinary ice. Its main characteristic is unique. When heated, it does not pass through the liquid state. It skips this step and goes directly from the solid state to the gaseous state, a phenomenon that scientists call sublimation. Because it doesn't generate moisture when it evaporates, dry ice is highly sought after for preserving food and medicine. Its mysterious mist has become a staple of special effects at shows and events, and its physical and chemical properties are so useful that it's also used for deep industrial cleaning. But have you ever wondered how dry ice is produced on an industrial scale? In this video, we'll discover together how one of the most fascinating chemical compounds is manufactured and packaged in factories. Stay with me until the end. Dry ice was discovered by accident in 1835 by French chemist Adrien Jean-Pierre Tillorier. Tillorier was working with liquid carbon dioxide in a high-pressure container. When he opened the cylinder, some of the liquid evaporated very quickly, and what remained turned into a solid white mass, what we now call dry ice. Despite this early discovery, its practical use didn't really begin until about a century later. It was in the 1920s that chemical companies in the United States began producing and marketing dry ice. At that time, it was mainly used to preserve food during transport, especially meat and dairy products. Its strength was that it maintained a very low temperature without leaving water residue as ordinary ice would. During the Second World War, its role became even more important. Dry ice was used to preserve vaccines, medicines, and food supplies for troops, contributing to medical and food logistics in times of conflict. What distinguishes dry ice from conventional ice is its direct solid gas behavior, sublimation, which prevents the formation of water and residue. Its extremely low temperature, around minus 78.5 degrees Celsius, makes it a preferred tool for refrigeration when conventional means are lacking. Its main function is to maintain materials at low temperatures where there is no refrigeration infrastructure. A notable example is the transport of organs for transplantation, such as the heart, which must remain at a very low temperature throughout their journey. Dry ice is also used to transport vaccines or any type of sensitive biological material. It's ideal for maintaining stable and safe thermal conditions. If you immerse dry ice in hot water, the carbon dioxide is released very quickly and creates a thick cloudiness, hence its spectacular special effects. But now let's look at how it's made. How do you get this otherworldly ice cream? It all starts with pure carbon dioxide, which is extracted and processed from various industrial sources. One common process is capturing CO2 from sugar fermentation during alcohol production in breweries and distilleries. This gas, produced in large quantities, is captured, purified, and then stored. Carbon dioxide can also be recovered as a byproduct during the synthesis of ammonia, a major component of fertilizers, and is captured before being released into the atmosphere. Some refineries also release CO2 when converting hydrocarbons into fuels and chemicals. It is even possible to recover carbon dioxide from the combustion of fossil fuels in thermal power plants. But be careful, CO2 from these sources often contains impurities that must be removed to ensure safe quality for dry ice production. The first purification steps involve filtering out solid particles and removing coarse impurities using mechanical filters. The gas then passes through scrubbers and other treatment systems where chemical compounds, vapors, and residual contaminants are removed. Once purified, the carbon dioxide is compressed to a pressure of about 15 bar, a pressure that corresponds to what one would feel about 150 meters deep under the sea. Under this high pressure, the CO2 is cooled to temperatures of around -20 to -30 degrees Celsius and then remains in a liquid state. In its liquid state, it becomes much easier to handle, transport, and store in specially designed tanks. The purified carbon dioxide is then stored in cryogenic tanks designed to withstand both high pressure and low temperatures. These tanks, often cylindrical and made of stainless steel to prevent corrosion, are equipped with valves and safety devices to prevent overpressure. They are maintained at sub-zero temperatures to limit CO2 evaporation. In some facilities, the total storage capacity can reach 2,600 tons of liquid carbon dioxide. From these tanks, liquid CO2 is transported by pipeline to the production units and specialized dry ice manufacturing machines. This is because carbon dioxide at high concentrations can be asphyxiating for workers. All facilities have continuous ventilation, alarm, and monitoring systems to control gas levels in the air and ensure operator safety. In the production machine, liquid CO2 is subjected to controlled decompression. The pressure is abruptly reduced to approximately 5 bar. This rapid reduction in pressure causes a sudden drop in temperature, resulting in the formation of carbon dioxide snow. During this expansion, the CO2 absorbs thermal energy from its surroundings and cools instantly. Some of it then becomes solid in the form of fine particles, known as dry ice, while another part becomes gaseous again and is evacuated through a ventilation system. The dry ice is deposited in a collection chamber inside the production machine. It accumulates as a white light, powdery powder, very similar to real snow. However, in its powdered state, it is not yet usable as solid dry ice. It needs to be compacted. To obtain solid blocks, the snow is transported to hydraulic fields that exert considerable pressure. Large quantities of CO2 snow are introduced into a rectangular mold. Then a hydraulic piston applies pressure of up to 300 bar. Under this stress, the snow particles bond together and form a compact and strong block. The block is thus formed at a temperature of approximately -78.5 degrees Celsius. It is then ejected from the mold and cut to the desired dimensions, according to customer requirements. Large blocks, smaller pieces, or pellets, small solid cylinders that are very practical for certain applications, can be produced. Pellets are generally manufactured in 2 common sizes: 16 millimeters in diameter for use in refrigeration and transport, and 3 millimeters for more specific uses such as dry ice cleaning. To make pellets, CO2 snow is forced through an extruder equipped with perforated dies. A mechanical piston forces the snow through the holes, and this pressure-driven shaping produces solid cylinders at the outlet. Depending on the diameter of the extruder's holes, pellets are obtained in sizes 16 millimeters or 3 millimeters. 16 millimeter pellets are often preferred for packaging and transporting low-temperature products. The finer 3 millimeter pellets are used for dry ice blasting, also known as dry ice jetting, or as raw material for making larger blocks. After compaction, dry ice remains at an extremely low temperature of approximately -78 degrees Celsius and must be handled and stored in a suitable environment to prevent premature sublimation. Since carbon dioxide is both an expensive raw material and considered polluting in some contexts, industries seek to recover and recycle as much of the gas released during production as possible to reduce losses and environmental impact. Once production is complete, the blocks and pellets are transported by conveyor to the packaging area. At this point, laboratory checks are carried out: weight, size, density, compaction. These are all factors that influence the product's strength and ability to resist fragmentation during transport. The product's purity is also analyzed to ensure it meets commercial quality standards. After passing these tests, the finished product is ready for storage and distribution. One of the main challenges associated with dry ice remains its transportation. Since it undergoes continuous sublimation, it tends to gradually disappear. To limit this loss, enormous insulated polystyrene boxes are used, real portable glaciers, which act like refrigerators and limit the conversion of the solid into gas. The goal is to maintain temperature and minimize sublimation, which can be around 5 to 10% per day, depending on environmental conditions, ambient temperature, insulation, container opening, etc. The final product is therefore packaged in its thermal containers, ensuring its preservation before distribution to customers, sometimes on the other side of the world. Because dry ice reaches temperatures close to -78 degrees Celsius, it is generally not necessary to place its crates in electrical refrigeration systems. Dry ice remains cold and solid on its own, provided it is stored properly. Dry ice is used in a wide variety of industries today. In the food industry, it ensures that food arrives frozen where it needs to be, from frozen products to perishable goods. In hospitals, it preserves vaccines, biological samples, and even organs intended for transplantation. In industry, pellets are used in cryogenic cleaning operations, allowing machines and molds to be stripped or cleaned without leaving chemical residue. And of course, in the entertainment world, dry ice produces the iconic fog that enhances shows, concerts, plays, and film productions. Thanks for staying here. If you enjoy this documentary, then don't forget to like, subscribe, and hit the bell so you don't miss any of our content.